You get it? Okay. Dear Heavenly Father, we thank you for this day. Thank you for these students. We thank you for the opportunity we have just to meet together and study your creation. And I just pray that you just encourage the students, if they had a bad day yesterday, to just keep on keeping on. There will be another day. In the name of prayer, Lord Jesus. Amen. I'm still very happy because I've not graded your test. Well, I mean, I don't know. Maybe they're all hundreds. Actually, that would be bad. I would want all 130s. That'd be better. Points are points, you know. Okay, so today we're talking about something a little bit different. Well, is it something different? I don't know. That's a question. It seems different. The way we solve these problems is different. So yeah, I guess it's different. But these are differential equations. Let me show you a few physical examples here to start with. Population growth. If you have P is the population and T is time, K is some positive constant, then what this equation, differential equation, says is that the time rate change of the population is proportional. The instantaneous rate of the population change is proportional to the amount of population you got there. So, when the population doubles, then the population growth rate is twice as fast, right? This is exponential growth, actually. But that's a differential equation. This is actually a first-order differential equation, and it's an ordinary differential equation because there's just one independent variable. Radioactive decay. My earlier section I was telling, it's kind of like analogous to what happened in the refrigerator in the break room close to my office over break. I don't know what's in there, but something's decaying. This is actually a little bit different. Like, you can't smell polonium or whatever. It just kills you. So, but radioactive decay is something we've observed in nature for a while now. There's certain particles that don't like who they are, and after so long, they just change to something else. And it's a random process. So the number of particles that are there, the more particles there are, the more decay you get, the more the number of particles changes. And that again is this differential equation. A more interesting one is Newton's law of cooling. Newton's law of cooling, what it says is if you do something like, say, put a cup of coffee in a room with air, right, as opposed to like putting a cup of coffee in a vacuum, that would be different and really painful without a spacesuit. But not for the coffee, but for you. The blood boiling and all that, not good. So what the Newton's second law of cooling says is that the temperature, big T, the rate of change is proportional to the difference in temperature between the object we're talking about, in this case, the temperature of the coffee, right, and the ambient temperature, the room temperature, R. The earlier section decided we were going to put a minus here and assume that K was positive. All right, that was our choice. It's just a notational choice. You could make another one. You could write the same differential equation in terms of like AT plus B, where A and big B are just constants. So the weirder notation is just so I can explain physically what's going on. So like, if this is a positive constant, think about it. If the temperature of the coffee is greater than room temperature, then the product minus K times T minus R is less than 0, right? Because you've got a negative times a positive is negative. So the rate of change of temperature is negative, right? Temperature decreases. I have a cup of somewhat hot coffee right here. It is not going to get hotter as I leave it on this table. That is the profound result of Newton's law of cooling. It actually is pretty profound that this is actually a pretty good model for that. That is kind of shocking to me. But on the other hand, if the temperature of the coffee is less than room temperature, what happens? Like if I had iced coffee, what would happen if I left it there for a long time? It would increase, right? Although I have a suspicion the ice, well, I don't know. I don't know about ice versus no ice and just cooled. What's the difference? I don't know. You have to find a good differential equations book to study those kinds of things. Let's see here. So, one of the differential equations book we had, it actually studies differential equations similar to this to understand the heat exchange of a house and the outside, and, like air conditioning versus heating. Different insulating factors give you different values of K essentially. So you can study it. But it's a differential equation. And so, of course, if the temperature of the coffee, if it's like iced coffee, then this is positive, right? Because the temperature of the coffee will increase. And what happens? Eventually, the solutions to this differential equation must do what? They must go to the ambient temperature, just physically speaking. So we'll learn how to solve this kind of differential equation. Another example would be population growth with carrying capacity. So this guy is like a modification of that one. Look what happens. So like this C is the so-called carrying capacity. What happens if P equals to C? What's dP dt? Right? What if P is greater than C? Yeah, it's negative. What if P is less than C? It's positive, right? I'm assuming, of course, that the population is not negative. I mean, I don't know what negative population is hard to understand. So if we study it for non-negative population, what you see is that all different populations, whatever your starting point is, they all drift towards this population of C, the so-called carrying capacity. All right. Various doomsday prophets have forecasted basically different carrying capacities for human population on Earth. They have all been wrong. All of them. We should never sacrifice the life of a living human for the sake of some hypothetical carrying capacity. I find it so offensive. Anyway, just a thought. I have a differential equations book that puts the carrying capacity of the U.S. at like 200 million. Oops. So anyway, population growth is a tricky thing, at least for human populations. Now, for bacteria in a petri dish or something, these ideas are more close to reality. All right, that's not math. How do you solve these? And just a little bit more general terminology. First order ODE in dependent variable y and independent variable x has form, this is going to be pretty vague, x, y, y prime equals to 0. So the reason it's a ODE, O is for ordinary, DE is for differential equation. It's an ordinary differential equation because there's just one independent variable. If you have more than one independent variable, then you have what's called a partial differential equation, or PDE. We can't study PDEs just yet because we don't know how to take derivatives in more than one variable. That's calculus 3. It is a fact that most of modern physics puts the basic laws of physics basically as partial differential equations, at least in the classical sense. So PDEs are important. ODEs are also important. As you can see, these are all ODEs. These are all, in fact, first-order ODEs. Let me show you some examples. So like dy dx plus x squared y is equal to e to the x. Or dy dx times x squared plus the sine of x times y equals to hyperbolic cosine of x plus 7 there. Again, a differential equation. First order. Yes, sir?
ODE stands for ordinary.
Yes, ODE, ordinary differential equation. Another example would be something like this. Dy dx squared plus y equals to 0, or the sine of y plus dy dx is equal to 0. I mean, you can just use your imagination. As long as the first derivative appears in a non-trivial fashion, whatever that means, I mean, those are all non-trivially appearing first derivatives. Don't make me define that for you. But you know it when you see it at the moment. All right, that'll have to suffice for us in here. These are all first-order differential equations, and they're all ordinary because they just involve one independent variable, x. In my physical examples, what did we have? Basically, x equals to t. So typically in physical examples, the independent variable is time. But because you guys like to calculate in x, we work with independent variable x for the math, just to get started with how to calculate things, right? When you actually go and put the techniques I'm teaching you into play, you'll have to change the x's to t's. That's not a big deal. Okay. Now, two of those differential equations are called linear differential equations. Two of them are nonlinear. Which ones are the linear? Which ones are the nonlinear? This is in fact linear. This is a linear ODE. First order, of course. The reason it's linear is because y and dy dx are appearing linearly. Again, this one is a linear ODE. It doesn't matter that there's nonlinear things in the independent variable. I mean, you can have sine of x, you can have cos of x. Those are horribly nonlinear functions. Doesn't matter. It's still a linear ODE because the linearity refers to the dependent variable and its derivatives. Okay? On the other hand, these two are hopelessly nonlinear. These are nonlinear. Well, there's some hope for the first one. I suppose I could solve for dy dx squared and take the square root. Then I'd get 2. Oh, no, still no good. I'd have the square root of y. It would still be nonlinear. So the reason I'm telling you about this terminology is it's important to understand the extent of what we can do. And what we can do in here, the first thing I'll teach you, what I'm teaching you today, is how to solve linear ODEs. Linear ODEs we can solve. All of them. As long as, well, I'll be more precise here in a second, but basically we can solve pretty much all linear ODEs. And it's nice. It's not hard. Nonlinear, well, not so much. These are, there's special solutions that are known for specific ones, and they're all kind of like their own little world, and there's no nice general theory, as far as I know. But linear ODEs are important. In fact, these are all linear ODEs, with the exception of this guy. Nonlinear, right? Because you got a p squared. But that said, in the first order case, we can actually solve a wide class of nonlinear ODEs by the technique I'll talk about next time. Next class we'll talk about separation of variables. In separation of variables, you can actually deal with a lot of nonlinear cases, but that's kind of a special first order thing. All right. So you're like, all right, well, math-wise, how are we going to solve these kinds of problems? I mean, this is very vague, right? But let's be a little bit. Well, let me add another example to the mix. It's an important example. It's one we've been dealing with already all semester. Can I erase these? Oh, I don't want to. Yes, I do. I'll make up my mind eventually. So another example which I should mention is this. The integral of f of x dx is equal to to y. That is a differential equation, but it's kind of in disguise, though. I guess you might not say that's a differential equation, but it's related to a differential equation in the following way. This is the same as looking at solutions to dy dx equals to what? How do you solve this for a given integrand? What are you trying to do? You're trying to solve the differential equation dy dx equals to what? Yeah. I know. I'm trying to find y such that dy dx equal to what? In my expression. F, right. See, these are the same equation, same differential equation, and it's just maybe I don't know, this is on the bubble of whether or not I would really consider a differential equation, and yet I want to say it's the same thing because after all, those have the same solution set. What's a solution? What's a solution to something on the left-hand side? Is, y equals to what? Say g of x such that what? I mean, I guess we usually use what? You usually use big F of x, right? Such that f prime of x equals to little f of x, right? But that's the same thing over here. A solution is what? It's like y equals to f of x such that what? dy dx equals df dx. I mean, this is just notational blah, blah, blah. I mean, my point is it's the same thing. So every time we integrate something, we're actually solving a differential equation. You've already been solving differential equations all along. You just didn't think of it that way, right? Here, let me be more explicit. The integral of x squared dx is equal to 1/3 x cubed plus a constant, right? Alternatively, I could look at this as dy dx is equal to x squared, right? Has solution. What's the solution? Is y is equal to 1/3 x cubed plus a constant. That's a solution because if I plug it into the differential equation, it works. Remember we had that homework problem earlier, y prime prime minus y. We showed Cauchy Cinch solved it. Same song and dance here. A solution to a differential equation is something when you plug it into the differential equation, the equation's true. And what's the solution set, by the way? Now I'm getting a little bit off track, but just hang on with me for a second here. 1/3 x cubed plus a constant such that c is a real number. So the solution set to this differential equation is actually an infinite family of functions, which are related by this additive constant, right? You just add a constant. If you think about their graphs, they're all vertical translations, one of the other. And you're like, wait a minute, you have infinitely many solutions over here. Why don't you just have one thing here? Well, I think that's really just a part of our custom. It would be really more accurate to say that the indefinite integral is this. Because the idea of the indefinite integral is to include all possible antiderivatives, not just one. Just like the general solution to that differential equation. Okay, so hey, that's one kind of differential equation we can already solve. So let's look at the problem of the linear ODE, and I'm going to walk you through the general solution here. So here's the starting point. We're given continuous P and Q, and we wish to solve, I'm going to call it star, dy dx plus py equals to q. So this, what I just wrote, folks, here, is a linear differential equation in so-called standard form. Oh, hey, now that we have this terminology, we can go back and we can look at the examples I already gave you guys, and we can play the game, what's P and what's Q? And is it in standard form? So this example here, if you look at it, what's my P? So we can, P is x squared, Q is what? E to the x, right? Now this one, that's not in standard form, right? Because something other than 1 is multiplying the dy dx. It's not yet monic. It needs a multiplier of 1. So I divide by x squared, and I get dy dx plus the sine of x divided by x squared times y equals the hyperbolic cosine of x plus 7, all divided by x squared. Now that I've done that, I've put it in standard form, right? And now I can tell you what the P and the Q are. This guy right here is P, and this character over here is the Q. And for my last example, those are nonlinear ODEs. They fall outside our realm. I say continuous, but in truth, this actually still makes sense for piecewise continuous. But continuous, we'll just stick with continuous. Okay, so now the next move is kind of shocking. Yes, sir? No? Oh, okay. We introduced something called the integrating factor. I'll follow your book. He calls it h. So we let h equal the exponential of the integral of p dx. To which you probably should be like, what on earth are you talking about? Why would you do that, right? Fair question. There are deep answers to this question, but none of them I can give to you here. It has something to do with the translational invariance of the differential equation. And this is part of a deeper theory of the symmetry of differential equations. But I probably shouldn't even say that. All right, so, I mean, basically you just have to trust me. All right, give me 2 minutes and I'll show you why this is amazing. So we calculate dh dx. What do we get? d dx of the exponential, right? So that's e to the integral of p times the derivative with respect to x of the integral, right? Why did I do this? What am I doing? We have e to the u, right? What's the derivative of e to the u with respect to x? It's e to the u times du dx. That's all I'm doing. It's just that the u here is a little scary looking. It's the integral of p. Okay? Oh, hey, but what's the derivative of the integral? What's this here? Yeah, that's just p. And what's this? Yeah, that's h, right? So we have just figured out this wonderful little identity, which is that dh dx is equal to h times p. I'm going to call that star star. All right. All right, so this integrating factor, it's formed from the exponential of an integral. But it's formed from an exponential. Exponentials are never 0. Exponentials are positive. I can multiply the equation star by the integrating factor without changing the solution set because it's non-zero, right? So multiply star by h, and what do we get? We get h dy dx plus hp y is equal to hq. You're like, well, okay, you're not convincing me that this h is worth looking at just yet. Fair enough. I haven't gotten to the punchline yet. Look at this, though. What is HP? The integrating factor times P? Yeah, thanks. It is dH dx, right? Times Y. And that's by star star. Because HP is dH dx. You guys with me? Star star is the identity right there. dH dx equals HP. So I'm just saying H times P is dH dx. So what? So look at this. Look at the thing I just got to. What is it? Derivative what? Derivative with respect to x of what equals HQ? We say HY. How did the gentleman see that? How do you get from here to here? Going from that to that is our beloved product rule from Calculus 1. Going down the board, you have what I call the reverse product rule. The integrating factor, multiplying by the integrating factor, makes the application of the reverse product rule not an accident, but an inevitability. It will happen. And I call this star star star, or triple star. Now, triple star brings me back to something of the form of my final example, which we already have had great experience solving already this semester. Some of us, our experience was more great than others. But we all know something about this example. And so, star star star, just integrate both sides, and what do we get? We get y, hy, is equal to the integral of HQ dx. So therefore, y is equal to 1 over h, the integral of HQ dx. And there you go. That is a solution to star for arbitrary p and q. But it's more than that. It's actually a method of solution. I don't just go through this because it's an arbitrary proof of a general thing. I mean, that's nice. That would be reason enough. But it's so much more than that. What I've just showed you is the thought process for how we solve linear ODEs. I don't just black box this formula and use it. That would be foolish. You could do it. I mean, that is a formula. All you got to do is calculate h, which is the integral of the exponential of the integral of p. Let's see how it works. Don't ask me questions just yet. See an example, then ask questions. Here's an example. dy dx plus xy equals to 1. First of all, that's a linear ODE in standard form, right? My p is x, my q is 1. Integrating factor, h, exponential of the integral of x dx. That's 1/2 x squared. Now, you might wonder, am I going to shoot you in the eye with this laser? You might wonder that. I won't, don't worry. Why didn't I add a constant here? Can anybody tell me why you don't need to add a constant in this calculation? Why it wouldn't change change anything? Well, it would still appear. I mean, if there was plus a constant here, the dH dx would still have like an e to the constant in it. Look at what we do in the last step. Eventually, we solve for y, right? And we solve for y. We have h over h, so like that would give you e to the c over e to the c, so it wouldn't change the final answer because you could factor out those e to the constants. Another way of looking at it is right here. It would be like multiplying this whole equation by e to the c. Then you could just divide by e to the c. So we don't need to add a constant in this integration. It suffices to just find an antiderivative. You don't have to find all of them. All right, enough talking about what we don't do. Let's talk about what we do do. So there's my integrating factor. What's my next step? Just like the proof, I multiply the differential equation by the integrating factor. That's my step. I'm sorry, it's been a long time. Let's see here. Where is it? So, really, this is step 1. This is step 2. Step 3 is down here. And this is step 4. Okay. Oh, I'm sorry. This was step 4. That was step 5. I'm just trying to mimic my numbering. But you follow the steps. It's the same steps. So I take the differential equation, I multiply by the integrating factor. That gets us to this, right? Now pay attention to this. If you have calculated the integrating factor correctly, you will be able to logically go from step 2 to step 3. All right? Check it out. I mean, if I take the derivative of this product, what do I get? I get e to the 1/2 x squared times dy dx, right? Fg prime. Plus, what's f prime g? Well, f prime would be what? It's the derivative of e to the 1/2 x squared, which is what? X e to the 1/2 x squared, which is exactly what I have here. So if I do the product rule on this, I get back to here. It's this reverse product rule. If you think through this, this gives you a check on whether you did step 1 correctly or not. If I have done step 1 incorrectly, the reverse product rule won't happen. All right? You'll think you have an integrating factor, but in fact you don't. So you go back to step 1 if that happens, all right? And then what? Then I integrate both sides, and I solve for y. And what I have here is the best I can do for this problem. This is a so-called integral solution. This is an integral solution. So what's an integral solution? Just what it sounds like, right? It's a solution of a differential equation or some other thing in terms of an integral. At this point, I will shut up and ask you if you have questions. Yes, sir.
Just step 2 right there. So can we just, like, let's say before we get down to step 3, just say, okay, what's the anti-equation with this? Similar to going like on, if you go by parts, you know, when you go from EV to B, you just do that for your part 2, step 2 and go to 3. That kind of sense.
Go from here to here?
Yeah.
Well, I mean, it is like integration by parts is just, basically integrating the product rule. So, but that's not how I think about it. I don't know. I mean, to me, it's just like I said, it's just the product rule in reverse. I mean, it is. So you're saying if you go back up to here and you integrate this, you can kind of look at this as integration by parts. I mean, that's true.
I already know that x e to the 1/2 x squared. I know that's going to be the times the dy dx, but the plus part where it says x times e2.
Mm-hmm.
If you integrate that, that should give you number 3.
I don't think so. The thing is, I don't know y yet, so I can't integrate this by itself because y is an unknown thing, and here's a integration doesn't usually work. Directly doesn't usually work. Here's another example of that. So if I try to solve, for example, I've got dy dx equals to y. This would be like exponential growth with constant 1, y equals p. All right? If I try to integrate both sides, right? I got it, with respect to x. Right? Okay, good. This is y. The thing is, I don't know why. I'm trying to find it. That's what makes the examples you've already worked so special, because we have the derivative is equal to a function of x. There's no y. The question is, what is y? We need to be just integrating isn't going to do it. We need to be sneakier to solve these. I mean, let me not leave you hanging. This example is really easy to solve. Don't get me wrong. This is what we're, and here's a fast forward to tomorrow. This is most of what we're doing tomorrow. So like dy over y equals to dx. Your book doesn't quite show you how to do it this way, so I'm kind of veering away from the book and just showing you what I always show people. I hope that's okay with you guys. This is separating variables. I put all the stuff with y on one side, put all the stuff with x on the other side. If you can do that, the equation's called separable. And then you just integrate both sides, and you get natural log the absolute value of y is equal to x plus a constant. Take the exponential of both sides of that, you get the absolute value of y is equal to e to the x plus c. Of course, that's e to the x times e to the c, and that's y is equal to plus or minus e to the c times e to the x. In other words, the general solution to dy dx equals to y is equal to k e to the x. Maybe I should say why not. I mean, why not? If you put in y with x equal to 0, you get back out why not. I mean, technically this is a linear differential equation, right? This one I just did. I mean, I can translate this. This is what, dy dx minus y equals to 0, right? So what's p equal to? P is equal to minus 1. And you can go through that song and dance. I will in a minute if we have time. And you can derive that from this machine. But it's like way easier to just separate variables. Separation of variables doesn't require this kind of multi-step technique. I mean, when I teach differential equations, I lead with separation of variables, and I teach integrating factor second. You're like, why are you teaching integrating factor first to us? We're just lowly Calc 2 students. Why are you doing this to us? Why? Your book has it in that order, and so I just followed the book. Sorry. It's not a good reason, but it's the reason. Okay. I don't know if I've answered your question or not. I mean, the real answer to your question, Steve, is just we got to do the reverse product rule. If we did it right, it will happen. Here's another example. Oh, any questions about that one? That's about as far as I mean. That's kind of it's not a very satisfying answer because it's left in terms of an integral, right? Which is kind of an unfamiliar thing to you guys. Sorry about that. This is example 3 from the text. Solve this xy prime minus 2y equals to 3x to the 4th. And here's a new wrinkle. We're actually given a piece of data, right? So if you're given an initial condition, you might be able to find like a specific function, which is the solution. All right, so same song and dance. First of all, I put it in the standard form, which is to isolate y prime. So it's now in the form dy dx plus py equals to q, right? What's my p? Don't neglect this minus sign. That minus sign is important. So p is equal to minus 2 over x. Does that make sense? Okay. So the integrating factor then is the exponential of the integral of minus 2 dx over x. Right? What's the integral of minus 2 dx over x? The integral is minus 2 ln of the absolute value of x. Be careful about absolute value. That matters here because we are looking at possibly negative values of x. I shouldn't neglect the absolute value. Neglect it to your peril in these problems. You'll lose cases. It matters. Usually. Now what? I use properties of the logarithm to bring the minus 2 up to the power, right? That's a property of logarithm that we all know. That we all know. That we all know. That we all should know. How about that? I think most of you guys know this. But knowing it and using it, those are two separate things, perhaps. Do you know to use it? I don't know. Okay, so there we have exponential of the natural log of the absolute value of x to the minus 2 power, but now exponential and log are inverse functions, so they... And then you've got x to the minus 2, which is 1 over the absolute value of x squared, but the absolute value of x is the square root of x squared, right? So you square that, you get back x squared. Or if you like, the absolute value of x is plus or minus x, right? So if you square it, you get x squared. You guys with me? All right. So the integrating factor for this one is 1 over x squared. So now I go back to the differential equation. I have now earned the right to do step number 2. We're now in step 2. We're going to multiply the differential equation by the integrating factor. So 1 over x squared y prime minus 2 over x cubed y is equal to 3x. Right? Because 3x cubed over x squared is 3x. And this is where the magic happens. This is the derivative of this product. It's the integrating factor times y. But again, we should think through this to make sure we didn't make a mistake in the calculation of h. If we differentiate this product, do we get back to here? Well, I definitely get 1 over x squared times y prime, right? Plus y times the derivative of 1 over x squared. What is the derivative of 1 over x squared? Minus 2x to the minus 3, right? It's minus 2 over x cubed. That's the derivative of 1 over x squared. Derivative of 1 over x squared is minus 2 over x cubed. In other words, this step is legit. That really is the product rule in reverse. You see why I say there's a redundancy built in here, right? If you do this right, this will make sense. If you do this wrong, this won't happen for you. I don't usually get to say this sort of thing as we're studying integration, right? It's not like you're doing trig substitution. Well, I guess it's somewhat true in a u substitution, right? If you can't get rid of stuff, maybe you know you need to do a different u. But you can kind of deceive yourself into being right, even when you're wrong. But if you really think through this, there's a quality check in this calculation. It's nice. Next step, I integrate both sides. The integral of the derivative is just the thing inside the derivative, right? So I get 1 over x squared times y, and then on the right-hand side, 3 halves x squared plus a constant. We have to add a constant here because I integrated in that step, right? What happens then? Now I can solve for y by multiplying by x squared in this case. And I get 3 halves x to the 4th plus cx squared. Now what I've boxed here is what's known as the general solution. The general solution to a differential equation, it's kind of like an insurance policy or something. I don't know. It includes all possible contingencies. Another way to look at it is the general solution. It's not really a specific solution. It's a family of solutions. For a first-order differential equation, typically the family of solutions will just be indexed by a specific constant c. And as you range over different values of this constant c, you'll toggle through different solutions. And, you know, that's also true over here. And these are pretty easy to graph, right? Like the solutions to this look like what? I mean, boring, or to quote my son, boring. I mean, they're just vertical translations, right? That's the solution. Those are typical solutions. As c varies, you trace over possible solutions. Here, I can't draw the picture. I don't know. I'm not sure what these, I know as C changes, you get different graphs. And I know from the theory of differential equations, those graphs will be disjoint. So they'll foliate the plane. If you take a particular point in the plane, there is a specific solution in this solution set which will go through that point by the existence and uniqueness theorem of ODE, of first order ODEs, which I will not state in here. Oops. Kind of just said it. Sorry. I will not state formally. There we go. Anyway, that's not the answer here because I'm given this specific data, right? So then I have to plug in what I'm given, which is that y of minus 1 is 2, to find the value of c. And so that gives me 2 is equal to 3/2 plus c, which gives me c is equal to 1/2. So then the solution, the specific solution I'm looking for here is 3/2 x to the 4th plus 1/2 x squared. Again, that's example 3 in the text. But any questions? We have till 10:10, right? All right, let's come back and let's work this example with the integrating factor technique instead of this hocus pocus separation of variables thing I did. Although I really shouldn't give it such a derisive moniker because I'm not really going to prove it for you tomorrow either. I mean, the reason this is valid is basically just the chain rule. It's a convenient notation for implementation of the chain rule in the same sense that U substitution is a convenient notation for implementing the chain rule of differentiation. So dy dx minus y. I mean, if you try to formally prove U substitution, it's really a drag. So we have p equals to minus 1. So h is the exponential of the integral of minus 1 times dx, right? So this is just e to the minus x. Well, that wasn't too bad. So you multiply this differential equation by h, we get e to the minus x dy dx minus e to the minus x y equals to 0. And that gives me, through the magic, well, it's not, I mean, I shouldn't really say magic. Well, we can call it magic, but if we call it magic, then you should understand that you're all magicians, because this is something you understand. Right? I mean, if you're Penn and Teller, is it still really magic if you understand it? I don't know. It's a question you can ask. Right? Is that step right? Think about it. Differentiate. Chain rule brings down to minus. That's it. This is even simpler to understand. This means that e to the minus x y is equal to a constant. Right? If the derivative of that's 0, it's a constant. That's a theorem in Calculus 1 even. Or you could integrate both sides if you like. Anyway, we get y is equal to c times e to the x, and there we go. Full circle back to what I got over there using separation of variables. I would argue separation of variables is easier because you don't have to remember this technique. You could argue, well, I have to remember that technique anyway because I just took your test, so I'm pretty sure if you talk about it, it's probably on the test. It's probably true. Probably true. But I don't know. I mean, whatever you like. All right, so tomorrow I will tell you about many things concerning first order differential equations, and then after that we will go to the second order case. We can actually solve second order differential equations pretty much with the quadratic equation. Isn't that weird? I shut up. Thanks, guys.